Okay. Okay.
Yeah, I'm okay.
Yeah.
Okay. Okay, good morning, everybody. So we'll get started. It's a distinct pleasure for Dr. Dan Stanzione to be here at OSU in person. Today, for the last 3 days, as some of you know, we had the MVP user group meeting in Columbus. Dan gave a keynote talk yesterday at that conference. So we are trying to optimize the travel. And we have the ICICLE EAB meeting today afternoon. So everything will work out here. So that's how he's in person. So I think most of you know him, but I'll just like to introduce briefly. He is the Associate Vice President for Research at the University of Texas at Austin and Executive Director of TACC, which is a nationally recognized leader in the high performance computing and has been involved in supercomputing for more than 30 years. His day job is to really design machines. Okay, so that's what his job is for the last 30 years. He's the PI for a number of the NSF supercomputers, including the current Frontera system, which is the fastest supercomputer at a US university, and is leading the upcoming NSF leadership class computing facility. So that's what we will be talking about. This system is called Horizon.
First system.
First system. So it's a series of systems. Will be deployed. And he received his bachelor's degree in electrical engineering and master's degree and doctorate in computer engineering from Clemson. So let's give a big welcome to that. So the hybrid floor is for you.
All right. Well, thanks everybody, both here in person and online. I think I'll just sit here so I can stay in the camera view for the Zoom broadcast. But yes, thanks very much for having me, TK, and the invite to come up here. And I did give an hour-long talk at MUG yesterday that some of you saw, so I promised that only about half the slides overlap. I'm gonna try to do something somewhat different, but some of the topics I need to repeat because for the ICICLE audience, I wanted to repeat a little bit about what the leadership facility is and tell you about it, and then some of the issues in supporting AI and sort of AI capabilities we want to build in and how we can get ICICLE and computer science here more engaged in what we're doing in the leadership facility, and then just talk about some other challenges in my usual soapboxes that I want to hit before we leave here. So yeah, so nice to see so many familiar names online and familiar members of the Invapich team here in the room. So yeah, and I should start off by saying part of our team at TACC is engaged in ICICLE.
Just a minute. So there is so Beth, you cannot see Dan and the slides?
No, I'm not able to. I see Harry's screen and then the slides, but I don't see the room.
Yeah. Just a minute.
It's got to switch. Yeah, do you see this Zoom?
Beth, I ended up just pinning Dan's picture that was able to see Dan then.
Oh, okay. Okay. All right. Yeah, thanks. Okay.
They see the slides, but they don't see.
Okay.
There we go. Okay, yeah. Okay, I see Dan. Okay. All right, I'm cool. Thanks. Sorry to interrupt.
Yeah, it's because the audio's not coming to Dan's mic.
I think they're fine.
Yeah, okay.
Yeah, because the slides. See them.
Okay.
Anybody else having difficulties out there in online space? Joe, Christian, you're my test subjects. So all good.
All good.
All good.
Okay, good. Sorry. Yeah. Sorry for
Got it. Okay, no problem. So yeah, so TACC, Joe and Christian, who are online, are part of the TACC team that participate in ICICLE. I think a lot of you know them and been very proud to be members of that. And of course, we've collaborated with the Invapich team for about 15 years now to have the performant open source message passing software on all of our production systems, and it's a requirement for every production system that we run Invapich on it, along with some vastly inferior vendor stack that has to sit there depending on the architecture. So so it's been a fantastic collaboration. So I'm really happy I could be here today in person at Ohio State to talk to all of you. And again, I think most of you know what about TACC. So You know, we provide a bunch of big resources, mostly funded by the National Science Foundation, Frontera, Stampede 2, Stampede 3 now, Jetstream, Chameleon, Lone Star, et cetera. We run about 20,000 servers. We have more than 1 million CPU cores across all the machines. I think we're now more like 1,400 GPUs, and steadily growing. But you know, we live at UT, but we're really a national center, right? I think on the big platforms, about 8% of our usage is UT. We exist to serve, you know, we actually went over 100,000 users in our history just this past year. Because our users are mostly grad students, they turn over at about 25 to 30% a year. So we add 8,000 to 10,000 new ones every year. To the systems, but you know, across 400 academic institutions, we really exist to be a national provider. We did add a couple of new machines this year, and I'll use these for some of the benchmark results I'm going to show you to support some of the things I'd like to talk about in sustainability. But Vista and Stampede 3, Stampede 3 is sort of a continuation of our Stampede line, which has always been Intel based and goes back to 2012. Was Stampede 1, and then we just retired Stampede 2, and Stampede 3 went into production in May with Intel Sapphire Rapids and some fun, the high bandwidth memory parts. Vista is our all NVIDIA system. I have specs on the next slide. So that is Grace Hopper, the NVIDIA ARM chip for the CPU, the Grace for the GPU. We have some pure ARM nodes, pure CPU nodes on there, as we're moving not just the GPU workloads, but all the CPU workloads over there as well. And with Lone Star 6, our AMD EPYC-based machine, we have sort of Frontera is our sort of older leadership class machine, 8,000 plus nodes, 500,000 cores, primarily CPU based. And then we have these sort of mid-scale newer machines, one in AMD, one in Intel, and one in ARM, that are informing our decisions for the next big one, which will be Horizon. And although I'm officially not supposed to talk about it because we haven't inked contracts yet, Horizon Plan A is that it will be the next generation of NVIDIA things. So a sort of evolution from Vista, although again, could change if things are delayed, either on the government side or the vendor side. But you know, we anticipate having roughly 1 million CPU cores in that machine, probably in Vera, which will be the successor to Grace, the next generation ARM chip. And then about 4,000 Blackwell GPUs is what's under the yellow embargo stickers. And again, they're just embargoed because if somebody looks this up later and I've changed it, I won't look as stupid. So down the line there. So, but yes, this next system is part of what NSF has done with their usual panache for words and acronyms, the leadership class computing facility. It's because Oak Ridge and Argonne have the leadership computing facility, and there can only be one in government. So I've got to figure out how to get rid of that class. The NSF just funded this after many years of planning on July 11th. And it will be hosted primarily at TACC, but it is a distributed facility with partners around the country. And, you know, it's something we've been working towards for a very long time. This actually was some semi-innocuous language in a solicitation that came out in 2017 that became Frontera. The value of persistence and long-term effort in projects, right? The solicitation was posted May 10th of 2017. We wrote the proposal and turned it in the Monday after supercomputing, which is the worst possible day to have a proposal due, and therefore all NSF proposals seem to be due then, on November 20th of 2017. And then with the start date of July 1st, which they didn't tell us about till 10 days later, it was just awarded last month. So it took 7 years and 2 months to get from the original proposal, which was to build a big machine, but to explore what a leadership facility would look like, and then actually getting up and running with the funding for it, which involved way too much time on Capitol Hill. So the reason this is important is, yes, it's the next big system, and that's awesome, and we like big toys. So to play with, and big computers for you to put all your work on. But it's really a change in the way NSF invests in computing. And so obviously it's a bigger scale system than Frontera, it's a bigger investment. So there's a scale up, but more importantly is they're changing the source of funding to what they call the Major Facilities Fund, which means one, a bazillion more review requirements. The actual design packages were around 4,000 pages. We had to go through 3 iterations of that. But it's putting computing on a par with the other NSF facilities, like the Large Hadron Collider and the LIGO Observatory and the Ecological Observatory Network, and 30 major facilities, the Vera Rubin Telescope that NSF invests in. And those things operate on the scale of decades, right? So, and traditionally NSF has been sort of a 4 years and gone model in funding systems. So, you know, you're a site, you get an award for a system. When that system ends, you may or may not have another one. And there's sort of, and somebody else may have it. They may want to do the same workloads that you did. They may not, they may change architectures. So if you're running the Vera Rubin Telescope and you're producing many petabytes of data over a decade, and then you need to curate and analyze that for another decade, none of the NSF sites were really reliable partners that were going to make it through a risk management review to say we can partner on the data. And with the LCCF, which, you know, has at this point about two and a half years of construction, 10 years of operations with a 10-year renewal option. You know, this is going out to the late 2040s. We may not own the contract the whole time. It could get reassigned to somebody else, but we can make these sort of 20-year commitments and have a persistent infrastructure to do, you know, really the sort of persistent computing services that we need to do science. So to me, yeah, the funding scales up is great, but the persistence is probably more important from a science perspective moving forward. So the LCCF is really four big things from a funding perspective. It's 5 if you count project management and the work breakdown structure, but nobody cares about that, but project managers and NSF. So we're building out a new home for the facility. It's a 15 megawatt initial build out on a data center with an option for 5 more. So we can go to 20 megawatts. There'll be a visitor center and all that kind of stuff. Space, there's the actual computing and storage systems that I'm going to say more about than I did yesterday, if you've seen this slide before. There's a software and services, including all the people that make this up component. It'll be somewhat distributed around the country. And then, of course, a big education and outreach component to keep the pipelines filled and the users coming for the system. So we do envision this as a distributed facility. In fact, we're working with, there's sort of 6 core partners and then about 10 more on applications. But so we have Frontera and now Vista available now for users. Horizon will be the next big system. Again, for some definition, it's 10x the capability of Frontera. We'll get into that. But there will be a quantum system and an accelerator test bed in Illinois at NCSA. There's a high throughput data and computing system, sort of look at high speed inference from instruments that'll live at the San Diego Supercomputer Center. We'll have our data mirrors and sort of storage and data curation systems at Pittsburgh Supercomputing Center. And then there'll be an interactive system really focused on accessibility, interactive computing, data science education at the Atlanta University Consortium. It's physically going to live at Morehouse College. And then we'll have people distributed across all these sites, plus a team at Cornell in education and outreach, and of course here at Ohio State on the networking software side. And then again, there'll be more sites announced for applications, but those are the sort of 6 core partners around the country that make up the facility. We dive a little bit more into the hardware for this. So again, if you measure FP64 flops, the gold standard for the top 500 list for sort of performance, you know, Frontera is about a 40 petaflop machine. Horizon will be around a 400 petaflop machine, so it is 10x in that dimension. But it's about 20% of that comes from the CPU side and about 80% of it comes from the GPU side. It turns out GPU flops are a lot cheaper to buy. So it's 20/80 in favor of GPUs for peak performance. Because of what we've seen in our application mix and what people are actually running, even with the infusion of AI workloads, in dollars, it's about 60/40 CPU. So that we could get to that 1 million cores and support the roughly 60% of our applications that we see that still can't use GPUs effectively. If you want to look at it as an AI machine, you basically multiply there's a 30-to-1 gap between vFloat 16 and FP64 performance on modern GPUs. So It's roughly a 10 exaflop machine from, AI tensor flops, if you want to look at it that way. And we didn't have these bfloat 16 instructions in the Frontera timeframe. So, it's effectively 100 times faster or 200 times faster from an AI thing. But even with all that capability, the core of Horizon still looks like a batch-based supercomputer, which you could also say is an AI training hardware, because they're essentially the same thing at this point, with GPUs, right? Tightly connected. By the way, it'll have a no oversubscription, fully connected InfiniBand tree, fat tree topology. We'll actually have two fat trees, one for the pure CPU nodes and one for the GPU nodes, and then a bridge between them fast enough to support the storage. But full bandwidth within all the CPU nodes, full bandwidth, no oversubscription within the GPU nodes, and it's only if you cross them that you'll have the potential to oversubscribe the network. So, but that's this sort of batch-based mode isn't the whole universe of computing by a long shot, right? And so we felt like to be a real leadership facility, we need some other systems as well. So we'll have a partition running Kubernetes or its spiritual equivalent, because these things do change over time. Just talking to someone this morning where it's like, yes, to support AI right now, all you have to do is make Torch and JAX works, and then you can support all AI. Except 2 years ago, it was TensorFlow, and 2 years before that, it was Caffe. So Torch forever, or 2 years, whichever. The history is every 2 years, everything shifts. So even though it seems like everyone will run TensorFlow forever, I'm like, yeah, but no one runs it anymore. But so we'll have this Kubernetes partition that'll run our interactive services, sort of the short-term things that require you to have availability, that are hard to do in a batch-based system, like Jupyter notebooks and all the interactive workloads for front ends and web portals. And then the other thing is the stuff that needs to run forever, right? And the persistent services, right? APIs, the so-called serverless computing, which I think is a joke, because try running it without a server somewhere. Server independent computing is probably a better name for that. And things like AI inferencing, right? Which is all done via API, but you need to have a persistent model sitting in memory to do that, right? And those things need to be on all the time, so you can't sort of batch schedule them. So we'll have a partition of the machine to do that. And then we'll have a whole host of data systems, because that's the other thing, the traditional HPC is you have home and scratch, and then you move to a tape archive. Data has a bigger life cycle than that, right? So we'll have about 5 tiers of data. We're going to do about 400 petabytes of solid state, all NVMe drives. I'm pleased to say I intend to have no spinning disk involved anywhere, because spinning disk is so incredibly painful, the scales they're at now with 30-hour drive rebuild times, that we're just going to get out of that game. So we'll have close to half an exabyte of solid state storage divided across the Scratch file system, but also a persistent, what we call collection file system, like our current Corral. DOI referenceable, online, hit it via the web in an S3 interface. Well, you can talk block, file, relational, however you want to talk to it. We'll have about an exabyte of archive space, because tape is still really cheap, and tape seems outmoded and ancient, but it takes 0 power at rest, and it costs less than 1/10 of what flash costs, and it keeps getting denser. You can buy a 100 terabyte tape cartridge in a couple of years. So, and we'll have support for controlled information. If you're doing patient research or human subjects research, we'll be able to support controlled and classified information across all the levels of storage and compute in the system. So that's a little more deep dive than the other talks have been on that. So we just got the construction funding. That doesn't mean bulldozers are moving anywhere, but the data center work, hopefully the data center will be announced today after several weeks of legal wrangling. So but you should see an announcement sometime this afternoon, I hope. But we're working with a co-location vendor to customize a data center. One of the great things about the AI boom is there's a ton of data centers under construction, and specifically in Austin where I need them. I like to say the main decision was the driving radius my lead sysadmin was willing to go, because if I go outside of that, I can't make the system work. So, so it's where Tommy will drive, determine where we could put them. But we actually ended up with multiple data center providers who are building big data centers right now, so we can sort of intercept them mid-construction. So if you start when you have to order transformers, it takes 4 years, right, to get them built. So we can't start at the beginning. You can get a system done in reasonable time. But if you wait till they're built, you have to tear up everything and redo the cooling infrastructure, because they're building from 10 kilowatt racks in some of these commercial data centers, and we're going to deploy 216 kilowatt racks into the space. So we need underfloor liquid cooling and, multiple cooling loops and all that kind of stuff. So we're grabbing a half-built data center and customizing it to meet our needs for turn it into an HPC style data center. So, but that means it'll be ready about October. And so the racks will start showing up in the fourth quarter of 2025. And we'll have users on hopefully in the beginning of 2026. And it'll be around for 5 or 6 years. 2031, 2032, and then Congress permitting, there'll be another round of systems after that. And again, the services will persist, but the hardware will get replaced every 5 years or so. So hopefully in the 20-year lifespan, we're looking at 4 different leadership systems and a lot of other peripheral systems along the way through the life of this. By the way, there is some intersection, although none official, with NAIR. There's the other big infrastructure project working its way through the NSF. Is the National AI Research Resource. It has a roadmap to spend $2.6 billion on of which 0 is currently appropriated. So there's a NAIR pilot underway, and the difference between pilot and production is production will have money from Congress, and pilot is everybody scraping stuff together out of existing budgets and existing hardware. So we have 47 NAIR projects on our systems now, but the $2.6 billion, it's unlikely to come in its full form at some point, and Horizon will have thousands of GPUs. So it is likely to be where a lot of the NAIR workload ends up living somewhere down the road or gets expanded for it. So I did want to talk while we're here in the department about how you might engage with the LCCF. It's maybe more relevant to the application side of ICICLE on the digital ag stuff and the pure CS. So just to be frank about this, right? The LCCF, we're primarily targeting computational science as opposed to computer science, right? The application-driven side. Although AI is beginning to blend all that difference. For pure computing research, we do have a CS testbed that we work with Kate Cahey at the University of Chicago on called Chameleon, which we've just got the next iteration of hardware on to upgrade, where we do, it's an OpenStack managed, you can get VMs or bare hardware, but we give users root. So if you want to do system software changes or something exotic that we wouldn't allow in a production system, Chameleon is the place to go, and it has lots of heterogeneous hardware. We have some FPGAs, we have all kinds of accelerators, we have DPUs in there now. So, so if you want to play with any of those things, Chameleon is the place to do that. It's also where we're building out a lot of the sort of edge sensor integration testbed. And talked to some of you this morning about some of that. How do we bring in things where the computing is partitioned between devices at the edge and devices at the core. So Chameleon, if you're doing sort of pure CS research, but there's still ways to get engaged with the LCCF, even in computing research. And again, AI is starting to look like both. But so we will have the ability to publish data and publish AI models through the LCCF. So if you want to reach an audience of thousands of scientists to use your model or your code, or seek adoption of your software, that will be a thing we can do pretty well, I hope. Certainly it's our intent. It's a really large test bed. And for those of you on the Mbappage team, we already run a ton of stuff on Frontera, trying to squeeze out as much scale as we can. If you need 1 million cores or multiple thousands of GPUs to run a test, we'll be a place you can do that without paying a cloud provider, tens of millions of dollars to do that. I will say, by the way, the big NSF projects, the major facilities and the institutes are our primary, sort of priority users. So as an AI institute, you get special allocation privileges on there. I am specifically looking for some more of these sort of large distributed instrument type projects, big sensor networks, big drone networks to partner with us, because sort of that whole what runs in the data center, what runs at the edge, how do you manage the data between them? There's a lot of open questions. There's no sort of standard way to do this. We'd like to build out that framework. So we're looking for partners. If you're, say, flying a drone fleet over farms and taking a bunch of imagery, with sporadic network connections, this is the kind of thing we're interested in working on architecture for, along with the SAGE project and some others. And once we get going, we will have some this is something we can't really spend money on in construction, but when we hit the operations phase, we'll always be looking towards next systems. We have some architecture research. We're gonna hear about some architects who are fairly well known, who are joining us fairly shortly to look at sort of next generation potential architectures. And so always happy to collaborate on proposals around that kind of stuff as well. So we hope you see the LCCF as a resource you can use, and not just this other thing that's out there. And again, you're a part of it through ICICLE, through Mbappage, but we're looking to bring in as many partners as possible because it exists to support the NSF funded community, essentially. So I want to switch gears a little bit and talk about AI on this. Obviously we've been sort of grappling with the use of AI in science. And there's about, AI for science reports or science for AI. There are dozens of National Academy reports. And there's a lot of, integrated workloads and surrogate models and things you see coming down the pipe. Where we'll have, generative AI for materials models and climate models and astronomy models and agriculture models. But I do want to just show a quick example that I happen to love of how we can use even the existing LLMs, right, whose job is to read and speak English, as AI assistants. When you start adding retrieval augmented generation and fine tuning to them, they can do some pretty remarkable things. That, if you're running a science lab, you have humans doing now that can automate in conjunction with your simulation workflow. I did steal this example from Rick Stevens at Argonne, but it's a pretty impressive one they did. So they gave an LLM, regular Gen AI, one of the open source models, a bigger one, 250,000 papers to read, and on a big system that took like half an hour for it to rag that in. And then they said, all right, I want to know about chromodomain helicase DNA binding protein 4. And as it turns out, as most of you probably know, Gen AI works better when you give it a lot of context and you make sort of complicated multi-step queries to get it thinking the right direction. And they asked it this series of questions, right? The plus line is, grab these papers, like using the knowledge that you were just trained on. Tell me, is this a well-studied gene? Are there open questions? Do you need it for survival? If it mutates, does it have an impact on phenotype? Does it have any drugs that target it? Is it involved in cancer? What do we know about its transcriptional regulation? And then in that last paragraph, the second question is to me the most interesting one. If you were starting out as a researcher, what might be the hypothesis you could explore related to this protein that would have significant scientific impact, right? So can it give you a research question? And now start thinking of hooking these things up to wet labs where they could run the experiments and come back and do it again in an iteration. So where possible, give concise answers and describe the function of the gene more generally. So here's the output. I moved my chat windows here, sort of annotated the text that came out of it to see, where each question. So it's moderately well studied. It's not really totally essential, but has some important functions. Neither the gene nor its encoded protein is directly targeted by any approved drugs. It's linked to glioblastoma and possibly some other cancers. It has known interaction partners with this other protein and this other protein and this other protein. Again, cancer links there. It plays an important role in transcriptional regulation through its involvement with this other complex. I'm not going to try and pronounce all the biology words here. But then that last paragraph, as a research oncologist, an interesting hypothesis to explore could be the investigation of CHD4 as a potential biomarker or therapeutic agent for glioblastoma or other cancers associated with its loss or mutations. That sounds good. I'm not entirely sure it's right. But if you think about this a little bit, if you have a big lab, what do you ask people to do, right? Go out, research a topic, right? Read a bunch of papers, know all the literature about it, and come back with a hypothesis. It's possible what this large language model is pitching is wrong. It's also possible if I asked grad students to go do this, they would also be wrong, right? If I asked a senior professor to do this, they might also be wrong, right? Because that's just sort of the nature of science. But if I asked them to read 250,000 papers and write me a summary, this took less than an hour to do, right? It's not going to get done in less than an hour. So you could argue that it's like coffee. It helps you, do stupid things and fail faster than you normally would. but we're all going to make mistakes and fail along the way. And if this accelerates the loop, there's a lot to be said with that. So this is just sort of a synthesis, give it a bunch of papers. It also can do extraction and distillation, right? Take a particular paper, write me a summary, tell me the hypothesis, whether the hypothesis is stated or implied, extract the hypothesis from the paper and it does a reasonable job, generating these kinds of reports. I did find out from a doctor recently that LLMs are really good at writing medical necessity letters to send to insurance companies. The doctors spend all their time where they're annoyed that somebody in an insurance company who has less medical training is saying this treatment shouldn't be approved to be paid for by insurance, and it will generate something complete with references about why it's important that's pages long, which means the insurance company people will just give up and do it. So I see this scary world where insurance is all done by two AIs writing bullshit back and forth over and over again, and that's how we decide to make payments. So none of that is actually necessary, but it's all going to exist. So, but it's really sort of amazing what we can do, even with just stuff that parses English and science. If it, you don't have to know quantum mechanics to be able to do useful things to accelerate the loop. So, and by the way, to do that at speed with a lot of people, where you're asking it to rag things like 250,000 papers, you're going to need a lot of inference ability, right? The tokens per second on that has to go pretty high, and you get to the point where thousands of nodes with thousands of GPUs are required to maintain that. So, hence the need for a dedicated inferencing platform, and some of what we're going to do with the LCC app. So, AI, wildly useful, whether we advance the models or not. Even today's models, we can do a ton, right? So, however, that means all the money is getting spent in AI hardware, and this is the soapbox, or the hill I'd like to die on before we go. You want me to stop about 11:45, right? So
Yeah,
somewhere in there.
Yeah, up to 12 o'clock. So.
Yeah, but we should take some time for questions. So,
Yes.
but I'm going to make my same pitch with a few less slides. But I would say to first order, every vendor is going to build chips that do AI well, because they're selling about $300 billion in hardware in the AI market and about $10 billion of hardware in the HPC market. And that's the kind of math that any CFO can do, right? 30 times more money in AI, right? Which is great in some ways, but the hardware vendors are going to go that way. And that means things like floating point performance at 64-bit isn't going to get any better, because nobody in AI cares, right? If floating point performance at 64-bit does. If you're trying to simulate the universe, you care a lot, particularly if you need to multiply small numbers by large numbers. Just by way of quick anecdote, I was sitting in a user meeting we had for Frontera recently, and different users giving different talks. And I realized that the scale of the grid they were using ranged from people measuring in angstroms to people measuring in megaparsecs. And the scale of the time steps they were using in their simulations went from picoseconds to gigayears. If you're doing galaxy evolution, how many billions of years did it take to get to that stage, right? So, which is a 10 to the 35 difference, right? So, not 2 to the 35, 10 to the 35. So if you ever have to multiply those two numbers together, 64 bits is nowhere near enough, right? To represent things at that scale. But if you're just trying to figure out, is this neuron connected to this neuron in a neural net, 4 bits seems to be more than adequate. So in fact, they really want 4.5 bits, because the neuroscience says there's 22 to 24 voltage levels your brain can get between neurons. And somehow they think with our billion-dollar machines, we should target, $20 an hour human is the goal. I don't know why that's the goal. I used to think we were trying to do better, but yeah, we're seeing this, focus on low precision. We're going to see hardware that isn't necessarily fitting into the scientific computing market. So my pitch here is we need to do the Beowulf thing again. I'm calling, there's AI for science. I want to do AI hardware for science. So at the end of the Cold War, we stopped doing custom circuits for supercomputers, gallium arsenide, high speed.
我让大家拉会儿琴呗，再继续拉一会儿我就好了。
Somebody's not muted. So, and there was this huge shift where a bunch of companies fell apart who were building supercomputers, Thinking Machines, Convex, Raytheon Supercomputing. There were a whole bunch. Most of them died or got dramatically downsized or acquired by somebody. But at NASA Goddard, 30 31 years ago, Thomas Sterling, Don Becker sat down and started the Beowulf project. And it was like, look, they're going to build microprocessors for PCs. That's where the money is. That's what they're going to build. We need to figure out how to use those to build supercomputers. And if we don't, we're screwed. So we're not going to have 1,000-bit vectors and long chain vector processing and some of the other stuff. Thomas said, what we needed to be was bottom feeding scum suckers. And these are the words of inspiration upon which I built my career. So it's to be a good bottom feeding scum sucker, but essentially use what the markets are going to build. And actually InfiniBand came out of that, right? Because we needed faster interconnects than the commodity markets, but we could use commodity chips to do it. And that has saved the AI marketplace that stuff existed. So silicon was expensive. We needed to use commodity parts. There were technology gaps, right? So Don at the time wrote the first ever network drivers, Ethernet drivers for this thing called Linux, which was this more or less academic toy that sat on a single box at the time. 99% of the internet runs on network Linux servers at this point, right? So arguably, Don did not make $1 trillion on this, but it's had, massive economic impact through the years. And then figure out how to use commodity processors. The precursors to MPI were born. 2 years later, MPI started. 6 years later, after that, Mbappage started. And since almost every top 500 machine, really every top 500 machine since 2005 is built this way. It was the HPC community that started using GPUs for computing, right? When CUDA got originally written, it was to say, let's take graphics parts and do science with them, right? So, and again, now all of AI is GPU-based computing, but if academics hadn't started, well, Ian Bucket was in NVIDIA when he wrote CUDA, but academics started this, let's find another way to use the cheap computing hardware to do stuff, because we're fundamentally cheap and we don't have enough funds to do what we want to do. So, bottom feeding scum sucker, remember, it's very important. So universities really led this transition. The agencies followed kicking and screaming. DOE still wants to do NRE with vendors to, make custom chips. But, and the vendors are like, if you don't have $10 billion, don't talk to us. But we can do this again, and we have a lot more to offer, right? The AI community needs low latency interconnects, right? To scale up their algorithms and train models. They're going to need to learn about sparsity at some point, right? And, people in numerical methods have been doing sparse algorithms for 70 years at this point. Everything we know about debugging things at scale, right, is incredibly valuable to those. So it can be a two-way street, but we need to do it all again. So, hence, I want to have the next Beowulf project, AI hardware for science. And to convince people that this is important, beyond the fact that we don't have any other choice, I think we need to tie it to sustainability. So let me say a bit about the sustainability angle on this. So historically, when people talk green computing, they're like, make your data center better. And that largely means better cooling technologies. But we've sort of gone, it's going to keep getting better, but it's not going to matter very much. And that it's not where most of green computing is going to happen, right? So, and I did run through all this yesterday, but cooling tech, we've made cooling a lot better, but mostly it's to deliver the kind of density that we actually need to deliver. Efficiency has been a pleasant side effect of that, right? But I don't have another way to run a 200 kilowatt rack. If I put 200 kilowatts in air, it would hit 180 degrees inside of 5 minutes, right? So I have to do liquid cooling, right? Or multi-phase cooling, or immersion cooling, or anything else to that, right? Because our chip densities are going up at a ridiculous amount, right? That's the Intel chips, the history of the Stampede systems, right? It was 130 watts in 2012. And by the way, then they said they were never going above 130 watts. In 2017, it was 145 watts. And they're like, well, we went over a little, but that's really the cap. And then in 2019, it was 210 watts. And now we have 350 watts. And the next one is 450. And it's going to keep going up from there. Meanwhile, GPUs have gone from 300 to 1,000 since 2019. The Grace 2 Blackwell modules that NVIDIA talks about a lot, but really won't start selling until next summer, are 2,700 watts a module. So put 2 of them in a server, you're at 6,000 watts for 1U. So, and that's how we're going to get to put 2 of them in 1U, put 36U of them in a rack. We're at 216 kilowatt per rack. So, so we're going to do liquid cooling because it's the only way to make the hardware work. But the impact, and we've gone through this whole immersion evolution, but like any other problem, Amdahl's law is technically a software problem about parallelism, but it works here too, right? Because basically Amdahl's law says, if 90% of your code can be parallelized and 10% can't, you're never going to make it go more than 10 times faster, right? Because you have that 10% fixed time. And if you could do the other 90% infinitely fast in the magic quantum machine, you still have 10% of the time, right? So your hard limit is 10. Turns out you didn't know about weak scaling, which is good for the rest of us. But let's think about this in the data center context, right? 10 years ago, 15 years ago, most data centers had a PUE of around 2, right? So for every watt you put into computing, you needed another watt for cooling, right? So you're only using 50% of your power to compute. By 2018, the average one was probably below 1.7. Everything built new. I mean, when we built Stampede, we hit 1.2 in 2012. Everything new is 1.2 or better, and there's a lot of things at 1.1, 1.09, right? So we moved all the data centers from 2 to 1.2. We reduced the amount of power it took to do computing by 40%, and that was freaking awesome, right? To go from 1.2 to 1.05 is like 10%. And to go from 1.05 to theoretically perfect no loss, which we'll never hit, is only another 5%, right? So if we're 5% from theoretically perfect, sort of what's the point, right? And that means, with 75 gigawatts of data center under construction, the terawatt hours per year, for any value of 1.x, we're not getting rid of the 1 in PUE if all we do is make data centers better. So I would say, if you really want to talk about efficiency, stop talking about data centers. It has nothing to do with it. And again, there's the argument that for scientific computing, we use big data centers to not only cause climate change, but to solve it and build new battery materials. It's a tiny fraction of the total power used as compared to, say, cat videos for transportation. So we can make the argument, but, and again, we have a totally green power grid. None of this argument would matter, but we can't unilaterally in computing change the way the entire power grid works. But there is things we can change. So again, we're moving to 100% wind credits. We just added a hydrogen fuel cell into our data center. We're looking at how we manage power with these fancy Grace Hopper modules, so I don't have to provision the whole thing. And renewables are coming along very quickly. April was the first time there was more power from renewables than coal in the United States. So can in fact happen. If we invest in the grid, it could happen a lot faster, but still. But Gen AI demand is adding the equivalent of Texas, and this is Texas in August. It's 107 degrees there yesterday. I'm not unhappy to be here, by the way. Totally unrelated note. But we're adding essentially the equivalent of 30 million people in 100-degree heat running air conditioners to the power grid just to do generative AI in the next 2 years, right? So that's just when current construction is completed. So it's huge. So to get real improvements in efficiency, we have to do the hard problems, which is better hardware and better software. And let's say for most of us, better hardware might be out of scope. So let's talk about software. So for instance, I mentioned GPUs, right? For peak flop, it's a lot cheaper, both in dollars and watts, to do it from a GPU than a CPU. But to make a very complicated argument short, it's because GPUs take out a lot of circuitry that protects programmers from themselves, right? And pushes the onus back to software developers, keep all those warps full, right? And make sure you're moving data in the right order through the streaming units. Whereas CPUs have, branch prediction, where they try and read your mind ahead of time and figure out what to prefetch for your code, and a lot on instruction decode and chip movement. But, if we're willing to do the software work to move to GPUs, I can get 5x. 5x is a lot better than getting another 10% out of my data center, right? Even the GPU codes are the good CPU codes. Most of them have an order of magnitude in them to improve. And we've seen time and time again, where we grab a code, and if I really make somebody pay full-time attention to it for a few months, we can get double, triple without changing the hardware at all, right? So same hardware, same power, but it runs faster. So we have, 1,000% potential to make software better. And even if we do a crappy job of it, we're going to outdo what really advanced data center technologies could do, because that's only going to get me 10%, right? Again, you see this is gigaflops per watt. and that, you know, the reason Frontier picked the MI250 from AMD, the current #1 system in the world, is it's 8 times better than the CPUs in gigaflops per watt. It just happens to be particularly nasty to program. So push the complexity to the software people, we can push efficiency forward. And again, yeah, right now, floating point operations takes less power than moving data 2 millimeters across a piece of silicon. So you actually analyze it, laying out data locality in the chips, all of this helps. But again, these simple AI accelerator parts mean all the work is on the software side, right? To use them efficiently, and not the hardware trying to help you out. But then you get simpler circuits and you use less power. So, so things we know, I mentioned this at the starting, right? If you look at an H100 right now, when you go to TF32, which is a perversion of the FP32 standard, where they change bits in the mantissa and stuff like that, but the good enough for AI tensor flops are 15 times faster than your double precision ops, right? And in 16, you're 30 times faster than your double precision ops. So even if you had a less efficient algorithm, even if it takes you 4 16-bit operations to do what you would have done in one 64-bit operation, a 4 times slowdown when it's 30 times faster, you get a 7x improvement, right? So, you know, there's a huge advantage in figuring out how to take advantage of some of these lower precision computations, right? And you know, there's a lot of other things that can happen, right? I mean, we've already seen as Moore's law is slowing down, we're starting to put faster memory in, right? Add HBM to CPUs. On our Sapphire Rapids, that gives us, on average, across the scientific codes we see, 2 chips, both running at 350 watts. The one with HBM will execute a workload 70% faster, right? So that's a 70% improvement in watts per science output, without having to change circuit designs inside the processor. So, and there's lots of other configurations. And this is one of the reasons we're willing to move to ARM at this point, is our benchmarking codes. Well, let me just cut to the numbers here. So this is 9 codes. Frontera, Cascade Lake is a 1, and speed up measured on your state-of-the-art Sapphire Rapids with HBM, which is in green, because I suck at colors. I have NVIDIA in blue and Intel in green. That's $10 billion in marketing down the drain on those things. I have so the blue there is Grace, then the Vista nodes are Grace Hopper nodes, but these are just the pure Grace parts, dual socket. The AMD, I'm giving AMD the short staff here because it's Milan, so it's a generation old. If I had Genoas, they would be much faster. So, but you see in raw performance, if I just look at a node, so this is 2 sockets of each one, right? Top bin, 2 sockets. There are codes like Amber where Grace is already faster than the Sapphire Rapids, but more often than not, the Sapphire Rapids is my fastest part, right? Per socket, it outperforms the Graces from NVIDIA. And again, wide workloads here. I have seismic codes, I have quantum chemistry codes, I have molecular dynamics codes, I have weather codes. If I divide by the power per box, the numbers, there's still 1 seismic code, AWP, where it's a ground motion code, where the Sapphire Rapids wins, but on the other 8, the Grace wins. Because it turns out, although I was comparing 2 top bin dual sockets, it takes about 1,100 watts to run that Sapphire Rapids box, and the Grace box uses about 550. So it's half the power. So if you care about time to first solution, power be damned, there's one solution. If you care about what's the least joules I need to get to my answer, you have a very different design point in terms of future architecture. So there's a group, just found this paper searching the web on green algorithms, but they came up with a carbon footprint measure for executing software and codes. So, you know, again, there's hard things we can do. Mixed and low precision, reduced ranked algorithms, using sparsity, coming up with higher order methods. But even if you just pick the right number of cores, you can make your efficiency a lot better. And this is something we'd like to incentivize users to do. So the green line there is your standard speed up that you see whenever you start throwing a lot of cores at a problem. And of course, for most codes, there's diminishing returns at some point, right? And there's more cores on the chip than you can effectively use. But your runtime keeps getting better if you use the rest of the cores. Your carbon footprint, however, starts going up when you use those cores less effectively, right? Because you're burning, you know, since linearly more power to get sublinear improvements in execution time. So if you just pick the right number of cores, which is going to force us to support multi-tenancy on the big systems to deal with this, and more containerization and more isolation of performance across the network cards and other things. But if we can do that, you can make huge differences in your science throughput for carbon output. So this is just an example from David Keyes in Saudi Arabia of looking at changing algorithms to take advantage of sparsity. And same hardware, 6-8x difference in runtime for just standard matrix operations, essentially Cholesky factorization. It just shows that current software, you can be a lot better than what's out there. So to make this happen, we're going to have to create incentives. We're going to start in the next year reporting joules with every job, how much energy you used. Probably socialize that for a few years, but then consider making that part of the allocation, right? If you use your joules more effectively, we'll give you more time on the systems, right? So to try and create an incentive for people to write sort of better software. But we're spending a ton of money on AI at the moment, one way or another, right? Both at the government level and especially at the private sector level, right? So if we start talking about AI hardware for science and sustainability and link those things together, and we say, we're going to exploit this AI hardware by writing better software. Really, it can be on any hardware. Again, the estimated spend on AI hardware this year is $300 billion. The Schumer blueprint for AI spending in government for the non-defense side is $30 billion. It'll never happen, but still. But if we took 1% of that investment and spent it in software, spent it in improving software efficiency and maintaining our code better, first of all, it'd be the biggest software program in the history of the NSF or anything else, right? Much bigger than ITR or any of the programs we've relied on in the past to do software, with 1% of the hardware investment. And you're not going to tell me that with, even if it was just 1% of the government investment, right? 30 billion, that's $300 million a year, right? The biggest software program we ever had. If you got a 10% improvement in the average efficiency of software, that's like buying $30 billion more hardware across that $300 billion. So that means, you need 30 billion less hardware to get the same workload done. You spent 300 million to get it. That's 100 to 1 return on the investment. So penny on the dollar to invest it. So, and funding software is the hardest thing to get government to do. So, again, this is my pitch that we'll use the leadership facility to move forward is we tie this to sustainability. One, we can do some real good. Two, we can actually get our software to work better, which has been a thorn in our side for decades, right? And get somebody to actually pay for making our software better because the return is huge. So, let me stop there. I think I've saved at least a couple minutes for questions, but thanks for having me. And I see we already have questions online.
Yeah.
So why don't I start there? Yeah.
Before we go to the QA, I actually forgot to mention one thing. I don't know whether you know, HPCware announced.
Oh God.
Those of you who don't know, like
This is another way to say I'm old after 30 years.
HPCware has 35 years completed, so they have announced 35 legends. And that is one of them.
Yes, apparently I'm a legend, which means it's greatly exaggerated.
So you can go to the HPCware page and you will see.
I'll say most of the people on the list, maybe not all, but a lot of them have done a lot more than I have in the field. However, they're also mostly dead at this point because legends are old, right? So, so I am still alive, so I might have the highest remaining pulse among the legends. But don't know if I deserve it, but I can win that part. So,
So there are some questions. Might be Eric. Please go ahead.
Yeah, thanks for a great talk, and I really appreciated this, especially as somebody is more on the end user side of things. I just wanted to marry two things that you said at the beginning and at the end of your talk. So at the beginning of your talk, you were saying you've got this rotating set of graduate students that are coming through, and that your user base keeps on flipping over and over and over again. And I really liked what you were saying about in terms of sustainability, thinking about, maybe we'll reward writing efficient code. So the question that I have is, do you have any plans or thinking about how to train students to actually write that efficient code, especially if they're not coming through the computer science pipeline. Because that's that's not an easy task.
No,
So,
it is not.
yeah.
And because I'm old and the legend, I think it may be an intractable task to some extent because programming keeps getting more complicated and we can't train students any faster, right? So, but I do think there's several pieces to that. One is, creating the incentives and the rewards, right, will help somewhat, right? Nobody has a reason, working on the science side. Those of you who work for DK, you have to get maximum performance out of your code, right? I mean, that's just a thing in the room. But if you're working on the code that solves your thesis, you have no incentive to make it go faster. You just want to get the answer and graduate. But if there were funding tied to it and there were, environmental goals tied to it, I think that will help to some degree. I do think we need to do a much better job of providing good abstractions, libraries, domain-specific languages to make this problem easier. And in fact, for all the criticism Apple gets for the walled garden around the App Store, they have slowly replaced about 65% of the silicon in the iPhone with hardware-specific accelerators. There's like 28 different accelerators for, speech processing and camera image processing. And the way they get away with that is they force you to use their APIs. You can't write your own numerical recipes, Fortran version of how to talk to a camera on an iPhone. You have to call the Apple API. So they can software emulate it when they want. They can drop in new hardware that's faster, and they can make it as complicated as they want behind the scenes, and you just call the API. Right. And so I think we're going to have to do, as we move towards domain-specific languages, we're going to have to hide some of this complexity. And AI is the place best positioned to it because, again, everything's tensor ops, right? You don't care how we do tensors, you just care that we do tensors. And there's not 900 ways to get to the tensor functions in the main libraries. But we have people who write their own FFTs all the time or their own matrix solvers and stuff like that all the time. So I can't put in a matrix specific accelerator because half the codes won't use it. So I think some combination of incentives and rules with continued but always hopeless attempts in education, maybe that combination we can move the needle some. So,
Song, please go ahead.
Thank you, Dan. This is a wonderful talk. My background is in the geoscience. It's great to hear your comments about the AI and with intersection with sustainability. So as you know, that recent discussion also talk about like green AI, emphasize like those sustainable and energy efficient AI model, especially for those large foundation model. I wonder, for putting the data center or those hardware perspective, what are the challenges, to kind of develop those green AI or those, putting those strategies, I think, in practice. So I think I'd like to hear your, insights. Thank you.
Yeah, I mean, there's a lot of pieces to that question. So let me just maybe hit a couple, and I don't have a good comprehensive answer, right? I know on the inference side, right, we need to look at ways we can reduce models and how fast we can swap them in and out, right? Sort of have a pots and spares because keeping all the models running on live hardware all the time is going to be way too expensive in power. But if I can, have them on local NVMe and do fast swaps and give you the impression of interactivity for inference rates for models that are least commonly used, we can do that. I know the sort of, the not multitude of experts, but or composition of experts, whatever MOE stands for at the moment. We found that using specialized small models and training them is essentially the clustering equivalent of big models, right? You get much more efficiency training 10, 100 billion parameter models than 1 trillion parameter model. But then you can merge the answers from those 10, 100 billion parameter models who trained on different parts of the data set and still get a best answer. And that, can reduce training costs and things like that. So there's going to be algorithmic pieces, there's going to be hardware pieces. And then there's just sort of the where you put the data center, which I think leads into Matt's question here. So.
Thank you. Let's take the last question, Matthew. Please proceed.
Thanks. Well, I do have the question in the chat about where you locate that and what you're doing with the heat that you're generating. But I also have a question. Totally unrelated. I just came back from working with the equivalent of the National Center for Bioinformatics in Japan, and there's large amounts of data sitting in global repositories for glycans and things like that. And I'm just curious what it looks like for international partnerships on this new hardware that you're building, and what that looks like in a more, if you could just sort of give some guidance on how to proceed with something like that to use your facilities. But still interested in your question that I put in the chat too.
And the question in chat on sustainability front, on co-locating, how are you reusing heat and things like that, boil water, heat rooms. So I do have the problem that I'm in Texas, right? So like there's the number 3 machine in the world, Lumi, is in Finland, and they do actually they use the old style heat pipes under the whole town, right? They use steam pipes into radiators and heat it, and they preheat the water off the data center. It's about a 25 megawatt machine, which gets them back about a third of their power cost, which is renewable anyway. There's 3 dams right by the data center. It's in Kajaani, Finland, which is a few hundred miles north of Helsinki. You didn't think there was stuff north of Helsinki, but it turns out you can fly north from Helsinki and go to Kajaani.
But you've had some cold winters lately.
Yeah, well, but it's 107 today, and that's the sort of standard summer temp. So yeah, heating buildings is actually not a problem we have, right? So I can't dump things there. What we are doing is raising the water temperature pretty dramatically. For us, we're going to 86 degrees as the inlet temperature on the water, because even without compression-based chillers, I can get 86-degree water a fair amount of the time. And our output on that's going to be well over 100. So you just sort of dump it in the air, which tends to heat the environment even more, but is a much more efficient way of using it rather than the 7-degree seawater, 64-degree water that we've been using, 42-degree water we've been using in the data center. So, but for this one, I need my sysadmins close to the hardware where we can kick it. We are looking at a longer-term project outside of the LCCF with DOE. So it turns out, because of our both that poor Texas grid and poor national grid, we have a ton of stranded renewable power. So if I move the data center 300 miles west, I have no water supply to cool it on in that deserty part of Texas. But there's 46 gigawatts of wind turbines and only 14 gigawatts of transmission lines. So if you can start, both running your data center and using excess free power from wind to crack hydrogen to store for fuel cells, so you can drop the load when the wind stops blowing. You can get power essentially for free and at 0 carbon. So, what we're going to do is buy all wind credits, but wind credits and wind are not the same thing, right? So it's close, but yeah, if you locate your data center,
You're not driving turbines or anything like that off essentially the steam you're producing.
Mm-hmm. No, it's unfortunately, it's not steam, right? Because it's coming back at about 120, right?
Right.
There are 2-phase cooling solutions where you do boil a different fluid, but then you need much wider hoses to move the steam out, and the condensers, balancing the condensers is really hard. You get better cooling because of the specific heat of doing the phase change. But yeah, the recapture rate, the efficiency is like below 10%. So yeah, I need to build some Olympic swimming pools near data centers, but again, the reservoir, the actual lake near Austin that is our reservoir, hits 92 by September most years. So as the ambient water temperature in the lake. So we don't really need to heat the swimming pools either. I got to figure out how to use it to cool stuff off. But yeah, great question. And the other part, yes. So because we are government funded, all of our projects need to have a US lead. But we only need to have a US lead. Foreign collaborators are just fine.
Right.
Not areas of restriction. And yes, for those big data sets, we're going to have petabytes dedicated to just capturing that data, so we don't have to move it over and over again. We may not become the official repository for a lot of it, but we'll have the work file system is just to park these big copies, so that you can compete against it without moving it over and over again and paying the cost of it over again. Yeah.
Great news. Thanks. Dan, great talk.
Yeah, so with this, let's conclude so that we remain on schedule for the remaining part of today. So thanks a lot again to Dan and for
Thanks for letting me know.
thank you. Thank you.
Thanks, everybody online.
Yeah, I think it is already disconnected.
Oh.
So.
Hey, Oh, yeah. Yeah. Begin and I'll get better.
Michigan. Yes. Yeah, it's easy. Thank you.
Thanks a lot. Nice to meet you guys.
Yeah, so you might be from Zoom also, or you did?
Yeah, I did. Yes, I'm out. Okay,
This show the room is not out.
1:30.
They're one.
Friday. Okay.
You, this thing where it shows.
Yeah, I said it's gonna, we've been over and
Yeah.
dropping the bottom.
Okay.